Well, hello all. Welcome to this interesting video session on multi-staging in launch vehicles. So, the introduction of multi-staging in launch vehicles we have already seen in our daily news of ISRO scientific space programs, where we have already a multi-stage rockets. It can be either GSLV or PSLV. Okay, so the idea is multi-staging is basically to have a velocity gain. Okay, throughout this mission. That is ultimate aim of providing staging to the launch vehicles of the rockets. Okay. Now here we have, let's say we take first and second and the third stages. The total stages is going to be three, and we have a payload here. Now each and every time in the mission, okay, at certain altitude, the propellant tank gets consumed off. Okay, the fuel in the propellant tank gets consumed off, and this weight is going to be the useless. Okay, it is no more useful bit. So this gets wiped away. Ultimately, this is going to get the second stage and and the preceding stages as well. So we have the second stage, okay, and now it will carry the payload, okay. Now this is going to be the payload, and up to certain height again, okay, the propellant in the second stage also getting consumed off. Now this also become very useless. Now this gets wiped away. So this is no more a part of this one. Now we end up with the third and the payload. Okay, the third and the payload. So I'll mark here P or something. So this will be a reference for you. So, and consequently in the third stage also your propellant gets wiped away. Okay. So ultimately your payload will be remaining. So which will be placed at the maybe at the orbit. Okay. So this is a mission which is been happening in case of a multi-staging launch vehicles. Okay. So this is a very valid point, and this has been already studied in a previous video. This has been explained by the Tsiolkovsky. So whenever you try to wipe away the masses, it is going to get the velocity gain. If it is a third stages rocket, it is going to get the velocity gain delta V1 at the first stage, delta V2 at the second stage, delta V3 at the third stage, and it keeps going depending on number of stages. Okay, the total ideal velocity gain is supposed to be the total velocity gain of the individual stages. So total will be your delta V1 plus delta V2 plus delta V3 up to delta Vn. Maybe we have a number of stages. So if you generalize this equation, we can write it is basically the summation of I equal to 1 to n. Okay, your Vn, delta Vn we can write. Okay, so this is the ultimate concept which is being employed in every space mission if a concept of staging is being involved. Okay, so the idea is you remove the extra masses or remove the unused or waste structure or weight mass. So because of the sudden removal of the waste mass, we are getting a velocity increment in the subsequent stages of the mission. Okay. Now, if delta V1 is being exhibited by ejecting this mass, then probably this is going to be delta V1. If this is going to eject, the second stage is going to eject, so this is going to be delta V2. Okay, and primarily, and again the lastly, if your third stage is also getting wiped away because the fuel gets finished off, so the structure gets wiped away, so this is going to be your delta V3. So that is going to push this payload further. Okay, so because of the delta V increment, it is basically creates an additional push to the rocket to move a bit faster. Okay, so the basic upside, though this is explained by the Skolsky rocket equation, which is already we have seen, that is going to be delta E is equal to C, and is effective exhaust gas velocity given by 1 by mass ratio. Okay, so mass ratio is nothing but the initial mass. It is basically final mass, okay, final mass of the stage divided by the initial mass. Okay, initial mass and the final mass. So that is going to be uh, the mass ratio. So if you again rewrite this equation, it's very interesting actually. You can write C into ln of your m initial divided by m final, or final mass and initial mass terms also you can write. So better clarification. Okay. Now we always try to remember one thing whenever we come across any sort of additional numericals, okay, any additional parameters or any additional stuff they are giving, you should be in a position to identify what is going to be the total net velocity gain. Now for that we'll try to explain this concept a little bit uh, detailed manner. Now let's say we have a three-stage rockets. Consider this as something similar to a GSLV, okay, having three stages. Now here we'll fix the payload. So here I'll raise the payload. Okay, and this is going to be the first stage. This is going to be second stage, and this is going to be third stage. Okay. Now, in every stages, the rocket is having some structural mass. Let's say this is going to be a structural mass, and this is going to be a structural mass, and we keep this as the mass of the payload. We write in this fashion. Okay, mass of the payload. Now every stages will have its own fuel. So this is going to be the mass of the propellant. So mass of the propellant, and here also we'll have mass of the propellant. Okay. So the total mass is going to be the sum of, okay, total mass is going to be the sum of mass of the propellant plus mass of the structure, and mass of the total in the second stage is going to be mass of the propellant plus mass of the structure, and here it is mass of the propellant plus mass of the structure, and ultimately we have the mass of the payload. Okay. Now my intention is to find out what is the velocity gain when the first stage is getting wiped away. Okay. So in that criteria or in that condition, what we'll do is like we go with a small concept here. Okay. Now we need to find the delta V1. So delta V1 we already know. So this is basically the effective exhaust gas velocity which is being exhibited internally by the first stage into the logarithm of m initial divided by m final. So I'll write in the short form. Okay. M initial and the m final. Okay. Now here we have a task. So in the first stage, if you're considering, then now let's say I'll write first stage here. The first stage, what is going to be my initial mass? It is basically the total mass, is it not? That is the starting stage. So it is going to be total mass. So this is going to be by m total, okay, of the first stage plus m total of the second stage plus m total of the third stage plus the mass of the payload. Okay. Now, as we are interested about the first stage, your final mass is going to be, okay, your final mass is going to be from all these masses, the final mass of the propellant is getting detected. So that means from all the masses, if you do, okay, mass of the payload, if you consume the fuel of the first stage, okay, now let's say this is going to be my MP1. Okay, your fuel is getting detected, so that is going to be my final mass of the first stage. Okay, so if you substitute this one, you are going to get the delta v1 value. Okay, if you know c1 and if you know the initial and the final masses, we are going to get the delta v1 quantity. So similarly, if it is going for the second stage, now the first stage is no longer present, so you can drop this term, so drop this stage, and now we are interested with the total mass up to payload for the second stage. Okay, your delta V2 we need to find. So in that condition, we take the second stage to the payload fully. So that is going to be my initial mass. So this is going to be my total mass of the second stage plus the third stage plus m payload. So here the propellant is getting consumed again. Now your final mass is going to be that entire term you can write. Okay, m payload minus you are going to consume the fuel inside the second stage. So this is going to be the mass of the propellant in the second stage. Okay. Now when it comes to the third stage, we do the same stuff. From the third stage, you have to consider the full as the initial mass. So this is going to be my initial mass is going to be my total mass of the third stage. Okay. Plus mass of the propellant, as this is no longer being associated with the body. Okay. So this get wiped away. So mass of the payload. Okay. And the final mass can be mt3 plus m payload minus the propellant which is being consumed of. Okay. Once you have the initial mass and the final mass, you can easily calculate the delta V1, delta V2, and delta V3 accordingly. Okay. So delta V1 is going to be C1 into ln of Mi by Mf. So delta V2 is going to be C2 into ln of Mi by Mf for the second stage. Okay. Similarly, C3 ln of Mi by Mf third stage. So if you add sum it of delta V1 plus delta V2 plus delta V3, you get the total delta V, which is equal to delta V1 plus delta V2 plus delta V3. Okay. Now this is a concept. Okay. This is a concept. And always you should also remember the thrust equation of the rocket in terms, we will try to explain this in a very easy manner. So the thrust is given by the efflux velocity or the effective jet velocity times the mass flow rate of the propellant. So we have mass of the propellant flow rate into effective exhaust gas velocity. So each stage will be having different thrust values. And if you know the amount of mass flow rate which is getting consumed, okay, we can find out the C value. Okay. In some cases in the real time we can take your thrust equation to be the mass of the propellant divided by the burn time into the C value. So burn time is the total time which the propellant gets burned. That is called the burn time. So mass of the propellant divided by the burn time into C will give me the thrust. Okay, so C can be found out. Your thrust into the burn time divided by the mass of the propellant of that particular stage. Okay, so this thing we have to keep in mind. Okay, so I think this concept is clear for you, and the only thing you need to remember is like when you consider the full stage, you have to count that stage itself. The complete stage you can count. Okay, when the fuel gets consumed up, that particular stage get unuseful. Okay, and that is getting wiped away, and so that not going to be a part of that particular launch vehicle. Now you start analyzing the subsequent stages, and accordingly you can detect the fuel and you can wipe away that term itself, and finally you end up with these kind of calculations. Okay, the ultimate aim is like you need to put this payload in the prescribed orbit. That is why we are using the launch vehicle. Okay, and whenever thrust is given in any sort of data, so you can calculate the effective or the flux velocity. Okay, accordingly, because rocket will be all having a total velocity or the effective velocity which pushes the machine forward, okay, for every stages, so which will be provided by the engine. Okay, for normally for high altitude operations we normally go for the cryogenic engines, okay, for the upper stages, and when it comes to the lower stages we normally go with the booster stages, is it not? So accordingly we can calculate the effective exhaust gas velocity based upon the thrust, burn time, and the mass of the propellant. Okay, I hope this is informative for you. So in the next session, we'll try to solve one numerical based upon the real time data, and so that you will get some more insights regarding the concept. Okay. I hope we have explained the Tsiolkovsky rocket equation applications on multi-staging aspect of launch vehicles. So I hope this is useful for you and try to practice accordingly. Okay. So we'll catch you in the next video then. Thank you so much.